Welcome back. This is the section 4.1 Introduction to Chemical Reactions mini booklet that you have, which marks the final part of the review. And this basically deals with balancing equations. So if we look here, chemistry is the study of substances and the changes that these substances undergo. These changes can either be physical changes or chemical changes. So highlighting that here. Physical change, of course, back from grade 10. Properties of a substance may change, but its chemical identity is the same. So you can cut up something into small pieces or changing state from solid to liquid, but it's still the same thing. So for example, expansion of compressed gas is a physical change, or dissolving salt in water, for example, that's a physical change as well because it's still salt. You can get it back by evaporating the water. So it's just a physical change. Chemical change, of course, results in the formation of a new substance, and it's extremely difficult to reverse. So for example, cooking, etc. involves chemical changes because you can't get the original ingredients back. They've changed forever. Okay, so the process in which one or more substances undergo a chemical change results in a chemical reaction. And also what you've done in Science 10 is looking at evidence of chemical reactions or indicators of chemical reactions. So sometimes a change in color indicates that a chemical reaction has happened. Energy, heat, or light given off, or it could also be absorbed. That is an indicator. A gas being produced, that's an indicator or evidence. And also a precipitate forming. If you have two liquids mixed together and a solid forms, that's also a good indication that a chemical reaction has happened. So as you can see, I'm getting you to highlight things in this textbook handout. The nice thing about the handout is that you get to write all over it, and you don't have to worry about getting in trouble for highlighting or writing in a textbook itself. Okay, so yes, it mentions here that yes, in cooking, you can see we have something new being formed, so it's a chemical change. Precipitate, again, a solid produced as a result of mixing two solutions. If you look at what happens to atoms in a chemical reaction, they give an example here of hydrogen peroxide breaking down. Hydrogen peroxide naturally breaks down. If you open up a bottle of it from the drugstore or supermarket, it automatically breaks down. But if you have it in the presence of manganese 4 oxide, it helps break it down even quicker. And the interesting thing here is that manganese 4 oxide remains the same. It acts as something to help the reaction, doesn't get changed itself, it remains as referred to as a catalyst. And also what we looked at in Science 10, if you're looking at balancing that hydrogen peroxide equation, what we have happening here, and with all chemical reactions, is that bonds of the reactants are broken down, they break apart, and then of course they rearrange to form new bonds. All the atoms that were present at the start must also be present at the end, but they're just arranged differently. And that makes sense because you can't make something out of nothing or lose something. So the total mass before the reaction must be the total mass after the reaction. So that's the law of conservation of mass. And of course, in terms of particles themselves, the kinds and quantities of atoms you had before must equal the ones after. So for example, here it is here. Hydrogen 2 molecules of hydrogen peroxide here. And we have it breaking down into, now I colored this to make it easier to see. The purple is oxygen atoms, and the blue are the hydrogens. So you can see here the hydrogen peroxide molecules break down to oxygen and water, and you can see 1, 2, 3, 4 purple, 1, 2, 3, 4 purple, 4 blue, 4 blue. So simply rearranged. Describing chemical reactions. So chemists have different ways of doing that, and we did that in Science 10 as well. Word equations versus chemical equations. Of course, we have reactants on the left-hand side of the arrow, products on the right. So let's think of it, things that react are reactants. We start off with that. They're on the left. Things that are produced or products, they're on the right-hand side. And of course, it's more beneficial to write a chemical formula because you can see the actual compounds and we can see the ratios in which they formed by looking at the numbers in front of the compounds, which indicate how many we have. Something that you may remember too, we have little shorthand letters to write the state of each compound. So if there's a little S after it, that means it's in the solid form. If it's L, it's liquid. G is gas, so you can see the three different states of matter. And a final one here is if it's a solid, liquid, or gas dissolved in water, it is an aqueous compound. So this just is showing here the word equation versus the chemical equation for hydrogen peroxide. Breaking down, so as I mentioned earlier, 2 molecules of hydrogen peroxide. You can use it visually by actually drawing them out or just putting the 2 in front. Of course, you see hydrogen peroxide is dissolved in water. Usually if there is a catalyst involved, it's written over top of the yields or gives arrow, showing that it's not in the, doesn't get rearranged, it's just there. And of course 2 waters, 1 oxygen. 2 waters, 1 oxygen. So you can see how that works out. And that equation is said to be balanced because the total number of atoms and type of each atom on the left is equal to what's on the right, just simply rearranged. Now, balancing equations we did in Science 10. Maybe not to the extent that we'll do them now. So if you remember some of the rules, write out the skeleton equation first. And by skeleton equation, all I mean is simply the equation without the coefficients in front. So you have to find out the formulas, etc., to make it work. Balance the atoms that appear once. It's easier to do that first than balance atoms that appear more than once. Treat polyatomic ions as 1 unit if you can. If they get broken down, though, you cannot do that. And then check. Another rule that I usually have said is that leave hydrogen until second last and oxygen until very last, because quite often you get oxygen occurring in more than one place. So if we look at a sample question here, sodium combining with oxygen to make sodium oxide, and of course here Hofbrinkel, we have oxygen occurring as O2. So if you look at the periodic table in my room, you'll see that clown on there, indicating all the elements that are diatomic. They occur as groups of 2 when they're by themselves. So sodium oxide, and of course we need 2 sodiums there because sodium's +1, oxygen's 2-, so we need 2 to balance out. Count the number of each, so of course you can see on the left we have 1 sodium, on the right we have 2 sodiums. Left we have 2 oxygens, 1 oxygen. So notice that oxygen was purposely left till the end. So we need 2 sodiums, so if we put a 2 in front there, you'll see that it doesn't work, because what happens here when we have a 2 there, we're short of oxygen on the right hand side. We need to have 2 of them, so we put a 2 in front, and then bang, all of a sudden you get 4 sodiums. So we put a 4 in front of there, and then it works out. But that's okay, do it in a series of steps to make it work out eventually. Yeah, I think there's another example here. Yes, copper and silver nitrate forming copper, 2 nitrate and silver. You can see that the NO3, I highlighted it here, stays together as a polyatomic group. So that's what I was mentioning here. Treat polyatomic ions as 1 unit if you can. If that had got split up though, you wouldn't be able to do that. So if we take a look here, we have 1 copper, 1 copper, 1 silver, 1 silver, and then 1 nitrate, 2 nitrates. So anything that we need to do is put a 2 over here to get 2 nitrates, and of course that's going to give us 2 silvers, but easily done. Put a 2 in front of that silver, and it should be able to work. And if we look at the next page, you'll see that's in fact what happens. Okay. Now I have a few practice questions that we're going to work on together here. In summary, Evidence of chemical reaction includes color change, absorption or release of energy, production of a gas, except evaporating or boiling. That's not considered making a gas. And formation of a precipitate. During a chemical reaction, reactant atoms are rearranged to form products. Chemical reactions are described using word equations and chemical equations. And a balanced chemical equation gives the correct proportions of chemicals in a chemical reaction. As a result, obeys the law of conservation of mass. Okay. Before we get to this assignment, we're going to work through this practice question together, these 6 that are involved here. So if I were you, I'd get a piece of loose leaf and just simply rewrite it. Give yourself some room here, because this is just too darn cluttered. You're not going to be able to fit anything in there. And also keeping track, just like over here on the bottom, there's simply not enough room. So you can see here on a separate piece of paper, write all the reactions, leave enough room here to put coefficients in front, and then underneath keep track. Okay, so maybe I'll have you write this out on loose leaf, A to F, try the first one, then tune into part 2 of the video to see how you made out.